Okay. All right, so let's start talking about some of the problems. So I think let's start with elementary number theory. So elementary number theory. So this is a huge topic. There's a lot of different things you can do. One of the things I love about this subject is it's easy to get involved. You can state these questions so well that somebody in kindergarten, well, depends who their father is or mother is. So somebody in kindergarten can understand what's going on. I've discussed a lot of these with Cam and Kayla and their classmates. Elementary does not mean easy. What elementary means is not using basically tools from complex analysis. It means, counting on fingers, which is one of the hardest things to do. One of the goals in counting is to try to find two different ways to count the same object. One way is the way that gives you the quantity you want, gives you the interpretation. And the other way is the way you can do. Okay, so we want to talk about perfect numbers. I think that was one of the projects. If anybody wants to referee a paper proving the non-existence of all perfect numbers or something like that, I'm sure I can find one for you from the submissions to the Journal of Number Theory. Can somebody tell me what a perfect number is? Almost. Some of its proper divisors. So n is perfect if equals sum of proper divisors. And there's lots of different notation people use. Sometimes they use the notation, sigma of n to represent the sum of the divisors of n. Sometimes they use tau functions to different powers to denote, are you taking the divisors to the first power, to the second power, to the third power? And so if sigma n equals 2n, then it's perfect. Sometimes, you might use like tau k of n to represent the sum of d to the k over all d that divides n. And so if you take k equals 1, that will give you just the number of divisors. There's a lot of great results known about the distribution of number of divisors of numbers. So how many of you have read Hardy and Wright's wonderful book? Okay. This is being recorded, so I can't talk about how you might be able to get access to that, so see me later. Hardy and Wright wrote a wonderful, wonderful book on number theory, and a lot of it is extremely elementary. And they have some remarkable results with really good results. So one question you might want to ask is, if n is big, that's a technical term, how many divisors? And then for those of you who are not doing this problem, what I hope you're getting out of this is at least thought process as to how you might attack things. So again, for small values, things can be misleading. So as an example of misleading, and for those of you who have been in class, you might even know what's coming right now, 40% of integers are prime, and 20% start a twin prime pair. Right? Is there anybody who has some suspicion about this statement? That 40% of all integers are prime, and 20% of all integers start a twin prime pair? Yeah, so if you check 1 through 10, you get 2, 3, 5, and 7. So that's 40% of integers are prime, and 20%, 3 and 5, start a twin prime pair. If you think that this is bull, you can double your range of computation. 11, 13, gets harder as you go higher up, 17, 19. Good, still 40%, and still 20% start a twin prime pair. No, I'm saying start a twin prime. So 3 starts one with 5, and 5 starts one with 7, 11 with 13. So 40% of all integers are prime, and 20% of all integers start a twin prime pair. And we even doubled the range of computation. Okay? No one should be convinced by an argument like this. We are all old enough that we do not consider 20 to be a big number. But for a lot of stuff, especially in projects involving L functions, there's a number called the conductor that describes the quantity we're looking at, and it's the log of the conductor that controls the spacing and the scaling. And the log of the conductor in a lot of the numerical investigations is on the order of 20. And just as we would never make conjectures, or should never make conjectures on primes based on the first 20 numbers, we should never be making these conjectures on L functions by just looking at quantities, even if the number themselves is huge. like 10 to the 15, 10 to the 16. That seems pretty big. But on a log scale, which is what's controlling what's going on, it's still a small number. So you want to be very careful as to what does big mean. Have you gone high enough to really see the limiting behavior? So over here, I'll be a little bit vague as to exactly what I mean by big, as to is big going to be accessible to us with computations? And so how many of you have good coding experience? Excellent. You really want to learn how to code. I like Mathematica. It's easy to use. It has a lot of nice graphical interfaces. It has a lot of great predefined functions. Being recorded, so I'll be careful. I almost view it like the singing horse. What's amazing is not that the horse sings well, but that the horse sings at all. Mathematica is not fast for a lot of number theory computations. And if you really want to investigate things, this is not the way to go. So for those of you who are doing more sums than differences, we don't want to write this code in Mathematica. We want to write it in a much faster environment. But Mathematica is very easy, and for a lot of investigations, we can start pretty quickly. For L functions, there's a great package called LCalc, written by one of my mathematical brothers, Michael Rubinstein. I think it interfaces well with Sage now. It's a great way to do a lot of stuff like this. Let's assume n is big. Then roughly, the number of prime factors is on the order of log n. And you've got to be a little careful as to what do you mean by the number of prime factors. So let's say my number is divisible by 17 cubed. Do I count 17 once or do I count it 3 times? Turns out it doesn't really matter that much. The number of distinct prime factors and the number of factors is on the order of log n. And I believe that there's a really nice result, I think it's the Erdős-Kac theorem, that the distribution of the number of divisors around log n for most numbers is, converges to a Gaussian. And we have a lot of results about stuff like this. So we have some understanding about how tau k is when k equals, for instance, 0. How many divisors are there? We have a lot of information. It's typically hard, though, to say things in particular about one specific number, because that number could have special properties. So can you give me any numbers that might have interesting properties when we want to count how many divisors? Okay, why factorials? They have a lot of divisors. There's actually maybe, so that, I mean, one question becomes, which number has the greatest number of possible divisors? So I want to maximize, is maximized. So one possibility is maybe n is a factorial. Another possibility might be n is a primorial. A primorial is like a factorial except you discriminate and you only take the primes going down. Another possibility is maybe you want high powers of small primes. Maybe you want to try n is 2 to the k. And so you might want to try to investigate certain quantities and see which one of these will give you the largest value of tau of n for n of a given size. Maybe for all n up to x, which n will give you the largest? What about the smallest? Where is it minimized? It's minimized for primes, yeah. For n equals prime. Can't really get smaller than that. The only divisors are 1 in itself. So the minimum is not that difficult. The maximum we could probably figure out without too much trouble. And what we then try to do is we look at the average behavior. And this is typically how progress is done. And this is going to be the same for L functions. This is going to be the same for random matrix theory. We give up on trying to understand what's going on for a specific item. We have some kind of central limit theorem. We say most things will be close to the system average. And we quantify what we mean by most, and we quantify what we mean by close. And so we can talk about what is the average order of functions like this. There's a great book of Weinitz-Kowalski where they go through calculations of average orders of stuff like this in a very accessible manner. I think Dirichlet's hyperbola method is used to calculate this in many cases. We can say a lot of things about on average. So for the project on perfect numbers, so let's see if I can move down here and stuff like yes. So we have the perfect number, n is perfect if it equals the sum of its proper divisors. So we had a couple of problems we could look at. So there's already almost perfect in the literature and near perfect is in the literature, right? And so this was actually, my interest in this began while waiting with my kids to watch The Force Awakens. Is, we weren't sure how many people were going to show up, so we showed up early. We had a lot of time to kill. And so I don't know exactly how we quite got to this conversation. Can somebody remind me what almost perfect is? Missing one divisor? Okay, so almost perfect is if we move one divisor, I guess, from the proper divisors. And then what was near perfect?
In the literature, that is near perfect.
I was wondering if this was, I thought this was near perfect.
Almost is when it's one less.
Okay, right. Near perfect is this, and then almost perfect is sigma of n is 2n minus 1. You are stuck with certain people's notations. So my advisor, Sanek, said that you will write sigma plus it when you refer to S for the Riemann zeta function, because that's what Riemann did, and until you prove the Riemann hypothesis, you will use his notation. This mixes Greek and non-Greek. In some sense, there's issues with that, but it's very understandable to do something like this. So we have near perfect, we have almost perfect. There's a lot of results about these. And then they've generalized near perfect to, I think, maybe k near perfect. If you remove k divisors from the proper divisors, and you get n. And we could probably also make, a k almost perfect. And one possibility is we could have it's 2k minus n. We could also say that sigma of n minus 2n is less than or equal to k. And so the original definition where it was 1 less, maybe we don't want it to be 1 less. Maybe we want to allow it to be either 1 less or 1 more. Or maybe to have it be within 1. So here's the question. Is a perfect number almost perfect? With this definition, yes. Right? And so you have to decide, do I want maybe something like this now? Or I guess probably I would want it maybe like this. So you have to think as to what is the right definition. In some sense, does it really make much of a difference? You can always combine them and do some bookkeeping. This is one of the most common problems in mathematics, is trying to figure out what is the right quantity to study, which is the easier one. There was a paper that Peter Sarnak wrote with Zev Rudnick, where Rudnick said it took them 9 months to come up with the correct combinatorial object to study. Sarnak said it took 6 months. I think maybe the postdoc was working on it for maybe a couple of months first. But a huge part of the paper was trying to figure out what is the tractable object to study. Which definition do we want? It may not be clear at first, but it might turn out as we're doing the arguments, do we want to allow a perfect number to be almost perfect? So we've talked about a couple of problems we could look at along these lines. So one interesting thing here is, question. Let's use this definition of k almost perfect. Right? Let's say if you're within k, we'll say you're k almost perfect. Does that seem like a reasonable definition? Does this seem like something worth studying? So what percent of n less than or equal to x are k almost perfect? So there's some results about this already in the literature. And I think we can start combining them. What we could then do is we could allow k to grow. What if k is a function of x? If k is large, the problem should be trivial. Give me a value of k of x where the problem is trivial. I don't care how stupid your answer is. Give me a really stupid answer to make the problem trivial. Well, it's going to be in terms of x. So you think x squared is sufficient? That the sum of the divisors, So x to the x should, I mean, to be really safe, something like that should be clearly safe, The sum of the divisors can't be this big. But worst case, every number less than or equal to x is a divisor of x, right? Not going to happen, but in that case, then if we sum all the integers from 1 to x, we get essentially x squared over 2. So your x squared should be more than enough. So we could do x squared, or maybe even 1/2 x squared, and we would be safe. So if we choose something like this, this is not that interesting. This is the level of triviality. Well, what if we then try to replace this as some constant x to the delta? For what delta can you prove that 100% of numbers are k almost perfect? Can you give me any numbers that will not be k almost perfect for fixed, for any reasonable k? Yeah, primes, okay? So whenever we have a prime, we're going to be in trouble. Or the product of two, so numbers that are a small product, we could have trouble. But there aren't that many of these numbers, and you want to get a sense of how many are there. So my question to you is, what values of delta can you say something meaningful? We already agree delta equals 2 is trivial. Can you get delta equals 1? Can you get delta equals 1/2? What about something like log the drowning swimmer x? If you put in 4 logs, are you safe? Huge part of number theory is these iterations of logs. Sometimes we use the notation log 4 of x. This does not mean we've all of a sudden shifted to working base 4. We're number theorists, we would never work base 4. It just means we have the logarithm iterated 4 times. So you want to be very careful when you're reading papers to understand what the notation is. So my first question is, what can you prove along something like this? How often is the sum within a certain fixed amount? And of course, we could ask the same question for k-near. Question. Same for maybe our new k-near. If we remove k factors, can we be within? So let's call it, you would need a good notation. Sigma, maybe negative k of n minus 2n, and maybe take the minimum over all possibilities. This is, you have to think a little bit about what you want the notation to be. How often can we get something like that? Any other questions that are just jumping out of people's minds as good starting points for this project? See, what I like is, I think something like this is you should be able to get some results fairly quickly. And you look at the literature, see what's known about the divisor function, see what's known about how many divisors you can have, how big could that sum be. And my feeling is you should be able to get a delta less than 2 today. If, of course, you actually have time to work today and not go to meetings. But does this give people some idea of how to start with problems like this? I love having free parameters. And you just try to see what's the best value you can get for this parameter. When you're doing arguments, it's often nice to say, I have a bound of this form, and then see how good of a result do you actually need to prove the result. Years ago, Andrew Wiles and I were supervising a senior thesis at Princeton. And the student was looking at the proof of what are the possible torsion groups of a elliptic curve over number fields. And there was a lot of heavy reading to do, and the student did not understand all the stuff that they were reading. And at one point, they needed to use the Weil bound for the Kloosterman sums in one of the proofs. And I asked the student, do you understand Weil's proof? No. They go, good, neither do I. It uses a lot of algebraic and arithmetic geometry that I'm not familiar with, but we don't need that. All we need is a simple, non-trivial bound on the Kloosterman sum, which you can get by counting on your fingers. And I can show you that simple proof, and that's all we need. Why do you think the paper used the Weil bound rather than the simpler bound? It's there. This is what the big boys and girls know. This is the best. This is the current state of the art. So they'll use that. Why use a weaker result? This is the best thing that's known. One of the dangers when you use the best thing that's known is you hide the difficulty and the depth of the problem. You make it look like this problem depends on far more cancellation than it really does. The other thing is if you're using a bound that's just been proved and it turns out that that bound is wrong, then all of a sudden you have to go, oh crap, how does this affect my argument? It's really good to see what is the minimum amount I need to actually have my result. Okay. Any other questions on this? All right, let's stop here for like 5 minutes and just, give yourself a moment to stretch.